Hi, my name is Tyler Bro, and this is Lab 4, Circuits and Capacitors. So we're going to start with introduction to concepts, then cover assumptions and models. We'll then discuss the details of the experiment, and lastly, the discussion. The purpose of this lab was to predict the behavior of circuits containing resistors in series and parallel. We used multimeters to measure experimental values of conventional current and potential differences, and lastly, compare experimental values to the expected ones by hand calculations. So a preview of the results is that the current in the two resistor circuit used was 0.02 amps. Calculated values and experimental ones line up. It was found that the greater the resistances in an RC circuit, the longer it takes for the capacitor to charge and discharge, and the time constant for the RC circuit we used was 2.786 seconds. Some key concepts include the node rule, IN equals I out, saying the current entering a junction will equal the sum of currents from each junction. The loop rule, delta V round trip equals 0, saying the difference in potential for a round-trip path is indeed 0. Resistance follows Ohm's law, V equals IR. Rearrange this to get R equals V over I. And lastly, capacitance, which equals Q over the absolute value of delta V, which also equals epsilon naught times area over separation. And this measures how much charge can be stored in a capacitor per unit of potential difference. The model used was on the Colorado PHYS simulator. So this was not a real circuit, these were simulated circuits. The system would be the ammeter or voltmeter, whatever was being used to measure, and the surroundings would be the circuit built. So now on to the experiment. You can see the first circuit set up here on the left, made of two batteries of 1.5 volts, two resistors, one of 47 ohm and 100 ohm, and two ammeters. The predicted current, you can see the hand calcs here, was 0.0204 amps, and the actual current was read to be 0.02 amps. Reversing the ammeter gave a reading of negative 0.02 amps, as the sign is reversed when the ammeter is reversed. Next, the same circuit was used, but the ammeter was replaced with a voltmeter. It was predicted that the voltage would be 3 and the current would be 0, and this is what it read, since this is now an open circuit. After closing the circuit with a wire instead of the previous voltmeter, the potential difference between the points shown in this diagram on the left were measured. The results are as follows, and these were then put into this little line graph shown here in the bottom left, and this does support the loop rule, as the sum of potential differences from A through H is 0. Next, this was reconstructed so that an ammeter would be in parallel with the 100 ohm resistor. The measured current increased from 0.02 amps to 0.06 amps, and this does agree with the expected values. Again, you can see the hand calcs below here, for where I sub A here, this ammeter should be roughly 0.06 amps, and I of the 100 ohm resistor should be pretty much close to 0. The resistance of each component was then calculated based on the experimental findings. It was found the resistance of the 47 ohm resistor was actually closer to 48, and for the 100 closer to 102. This will be discussed later. Next, an RC circuit was created with a 10 ohm resistor being the bulb, a 200 capacitor, and a 9 volt battery. The time was then measured to charge and discharge the capacitor, and then replaced with a 20 ohm resistor. And the results of the average of 3 trials, roughly 10.3 seconds to charge and discharge the 10 ohm resistor, and 19.8 seconds to charge and discharge the 20 ohm resistor. You can see it roughly doubles for doubling the resistance, showing that a greater resistance is a greater time to charge. The battery is then removed, bulb resistance was up to 30 ohms, creating a new circuit. Potential was measured once per second over 20 seconds, and then natural log of potential over initial potential versus T was plotted as shown on the left. And to get the value of the time constant is simply -1 divided by the slope, which gives us 2.786 seconds. You can see it's the slope of the linear trend line of this graph. So model discrepancies, the resistance calculated was actually higher than the listed due to the imprecise ammeters. They only went to about 2 decimals, so if they were more precise, then we might have found this value to be closer. Sources of error are few since this was a simulated experiment. However, it could include precisions of the ammeters, rounding in calculations, and timing error in determining the charge-discharge times. If this was done in real life and an ammeter was used, this would slightly decrease measured current readings, as real ammeters have non-zero resistance, as do the wires. And if real batteries and capacitors were used, the ideal model predicts that the capacitor charges nearly instantly, whereas the non-zero resistance of real wires and capacitors would increase the time to reach full charge. Thank you.